physics homework. And I would like to, I should be prepared before we have to prepare that.
That's not how I feel. I don't know if I love it. But at least it was not Friday. What's this? Just a fair question. Oh. Nice multiple choice.
So continuing some of those concept questions from Fudge. Those are the good answers. Concepts, all the math problems that seem to have screw ups.
I feel like it's not gonna be that difficult, but the last physics I've done was the really hard problems that took half an hour to do. So I just don't feel. But that's not gonna be complex, so.
We'll start in a minute. Today we'll be in section 11.3 on the integral test and estimates of sums. So this has to do with infinite series. Okay, starting at the top, determining what a convergent infinite series converges to is generally more difficult than determining whether an infinite series is convergent or divergent. But under ideal conditions, the integral test can be used to determine if an infinite series is convergent or divergent. So when applying the integral test, you have to make sure that certain conditions are met. So suppose a function f is continuous, positive, and decreasing on the interval from 1 to infinity. And suppose that a sequence a sub n is equal to f of n whenever n is a positive integer. Then the series of the a sub n terms, as n ranges from 1 to infinity, is convergent if and only if the improper integral of f of x from 1 to infinity is convergent. So another way to say that is, if the improper integral of f of x from 1 to infinity is convergent, then the corresponding series of the a sub n terms is also convergent. But on the other hand, if the improper integral of f of x from 1 to infinity is divergent, then the corresponding series of the a sub n terms is also divergent. So we'll go through a pictorial argument of the integral test. Case 1, suppose that the improper integral of f of x as x goes from 1 to infinity is convergent. So we'll sketch a possible graph of y equals f of x. And we'll divide the x-axis into subintervals, each of length 1. And then we'll construct rectangles. So remember what it means if the improper integral of f of x from 1 to infinity is convergent. What does that mean? That means that the area that's below the graph of y equals f of x and above the x-axis from 1 to infinity is a finite number. Okay, so we're going to construct rectangles that are below the curve. The area of this first one on the left, well, remember what this point is. It's f of 1, but f of 1 is a sub 1. It's the first term in the sequence a sub n, right? So this ordered pair is 1 for x and a sub 1, which is f of 1. And so the area of this first rectangle is a sub 1, because the height of that rectangle is the y-coordinate a sub 1. The area of the second rectangle is a sub 2, and the area of the next rectangle is a sub 3, and so on. So we can say that if we add the areas of those rectangles, a sub 1 plus a sub 2 plus a sub 3, and so on forever, it's going to be less than a sub 1 plus the improper integral from 1 to infinity of f of x dx. So why do you suppose I put the a sub 1 plus the improper integral on the right-hand side? Don't know? Okay. Well, the improper integral of f of x from 1 to infinity, that is just this area. But we're starting the rectangles to the left of x equals 1. So if I just add that area to this, and the other rectangles are below, well, all of the rectangles are below the graph of y equals f of x, then this infinite series is less than a finite number plus a finite number, because this is convergent. So a sub 1 plus this indefinite integral, sorry, not indefinite, improper integral of f of x from 1 to infinity, that's equal to a finite number. I'll just call it m. And so we can conclude that the infinite series of the a sub n terms is also convergent. So a couple of more things about the argument. Remember what the sequence of partial sums is. S sub n is the sum of the first n terms of the sequence a sub n. And S sub n is, or I should say the limit of this sequence S sub n is equal to the infinite series of the a sub n terms. But the sequence S sub n is increasing and bounded above. So just note S sub n, the sequence S of the partial sums, is increasing and bounded above and so by the monotonic convergence theorem, the limit of S sub n exists. And so since the limit of the sequence of partial sums is equal to the series, we say that the series converges. Hey, did you follow that, what I'm trying to say? So this is equal to some number S. We'll say that S is the limit of the sequence of partial sums, which is also the what the infinite series converges to. Okay, on the other hand, if the improper integral of f of x from 1 to infinity is divergent, we want to argue that the infinite series of the a sub n terms is also divergent. So we'll do another sketch. So f of x is positive, continuous, and decreasing from 1 to infinity. So this time we want to construct our rectangles so that they are partially above the curve. Okay, so the area of this first rectangle is a sub 1. The height of the rectangle is f of 1 equals a sub 1. And since the base length is 1, the area of that first rectangle is a sub 1. The area of the second rectangle is a sub 2. The area of the third rectangle is a sub 3, and so on. But the improper integral is below the rectangles. So the improper integral is less than the infinite series. And the improper integral diverges to infinity, so that must mean that the series also diverges to infinity. Okay. So the thing to remember if you're trying to show that an infinite series converges or diverges, well, under these special conditions, you can use the integral test. Okay, the next page. If p is a fixed real number, then a series of the form 1 over n to the p, where n ranges from 1 to infinity, is called a p-series. And we'll identify for which values of p, a p-series is convergent. So first, if p is less than or equal to 0, then we know that the limit of 1 over n to the p does not equal 0. And so those p-series are divergent by the test for divergence. So if you still haven't really mastered the statement in the test for divergence, make sure that you do so. It's not too hard to understand, but it's important and very useful. If p is greater than 0, then f of x is equal to 1 over x to the p is continuous, positive, and decreasing on the interval from 1 to infinity. And so the integral test can be used to test for convergence. Okay, but we've answered this question before in section 7.8. In that section, we saw that the improper integral of 1 over x to the p, as x ranges from 1 to infinity, this is convergent if p is greater than 1 and divergent if p is less than or equal to 1. Okay, so we can conclude by using the integral test. The p series, it's an infinite series of 1 over n to the p as n ranges from 1 to infinity. This will be convergent if p is greater than 1, and it will be divergent if p is less than or equal to 1. Okay, so on this first example of using the integral test, we're going to show that the p series of 1 over the cube root of n to the 4th as n ranges from 1 to infinity will show that it converges by using the integral test. Okay, so the corresponding function f of x is 1 over the cubed root of x to the 4th. And that can be written as x to the negative 4/3. So this function f of x, so we note that f of n is equal to 1 over the cubed root of n to the 4th for natural numbers n, or for positive integers n. We also note that the function f is continuous and decreasing, and it's positive on the interval from 1 to infinity. So it satisfies the conditions for using the integral test. Okay, so we compute the improper integral from 1 to infinity of x to the negative 4/3 dx. But we write this as a limit. I'll use the variable t as the limit as t approaches infinity of the definite integral from 1 to t of x to the negative 4/3 dx. So this is the limit as t approaches infinity, an antiderivative of x to the negative 4/3. X to the negative 4/3 plus 1 is x to the negative 1/3, and then divided by negative 1/3 from 1 to t. So let's rewrite that expression first. The limit as t approaches infinity. A more convenient way to write this, at least in my opinion, is to write it as negative 3 over x to the positive 1/3. Evaluate this from 1 to t. And we get negative 3 over t to the 1/3 minus 3 over 1 to the 1/3. I should say minus a negative 3 over 1 to the 1/3. When we allow t to go to infinity, this term goes to 0. The denominator gets large, so the term goes to 0, and the limit is the negative of negative 3 over 1, or positive 3. Okay, so according to the integral test, this infinite series converges because the improper integral converges. Okay, the next example used the integral test to show that the p-series sorry, this is not a p-series, but it is a series that we can use the integral test for. So use the integral test to show that this series converges. Okay, so the corresponding function is f of x equals the arctangent of x divided by 1 plus x squared. Okay, for x greater than or equal to 1, f of x is positive and continuous. So how do we know if it's decreasing on the interval from 1 to infinity? Do what?
Plug in x values. Plug in x values.
Right, at what value?
Plug in x values.
Oh, well. Yeah, but how do you know for all of the x values that you plug in that it is going to always decrease? One of the techniques for showing that a function is decreasing, to show that f of x is eventually decreasing, it might not be decreasing for a little while, but as long as it starts to decrease forever after a certain point, then we can still use the integral test. But to show that f of x is decreasing, show that f prime of x is negative. So I am not going to do that here, but you can show that f prime of x is decreasing after x equals pi over 4, I think. Okay, so we're going to take a look at the improper integral from 1 to infinity of the arctangent of x divided by 1 plus x squared dx. Okay, so here if we use a u substitution, if u is equal to the arctangent of x, then what's du?
1 over 1 plus x squared.
Yeah, the derivative of arctangent of x is 1 over 1 plus x squared dx. So all of that appears in the integrand. So we can transform this integral to, the integrand will be e du. And what will the limits of the integral be? Well, when x is 1, the u value is the arctangent of 1. And the arctangent of 1 is pi over 4. And then if x approaches infinity, what does arctangent of x approach as x approaches infinity? Pi over 2. So up here I'll sketch the graph of arctangent of x. The arctangent of x looks something like this. This is y equals pi over 2. So as x approaches infinity, arctangent of x approaches pi over 2. Okay, so you can see that this integral is going to have a finite value. So you square it over 2 from pi over 4 to pi over 2. So we've already done enough work that we need to do. Okay, but that's a finite number, so using the integral test, this infinite series converges because the improper integral converges to a finite number. Okay, the next part, estimating the sum of a series. So let's let f of x be a continuous positive decreasing function such that f of n equals a sub n for each positive integer n. And we'll suppose that it has been shown by the integral test that the infinite series of the a sub n terms is convergent, and that the infinite series is equal to s, which is equal to the limit of the sequence of partial sums s sub n. Okay, so for each positive integer n, an approximation of the infinite series of the a sub n terms is the sequence of partial sums. So in other words, S sub n can be used to approximate the infinite series. So I'll just remind you again, S sub n, what's S sub n?
The sequence of partial sums.
Yeah, a1 plus a2 plus dot, 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 up to a sub n. It's the sequence of partial sums. And the larger the n, the better the approximation, as you would expect. Okay, so here we have a new definition. The remainder of the approximation S sub n is defined to be capital R sub n equals S minus S sub n. So S is the sum of the infinite series. It's what the infinite series converges to. And if S sub n is used as an approximation for the sum, then the remainder is S minus S sub n, which just amounts to the terms a sub n plus 1 plus a sub n plus 2, and so on. That's the remainder. The remainder is the error made when S sub n is used to approximate the sum. Okay, so we're going to note that the improper integral of f of x dx from n plus 1 to infinity is less than the remainder r sub n, which is less than the improper integral of f of x from n to infinity. Okay, so in this space, I'll draw a couple of graphs to make this argument. So we have some function f of x that's continuous, positive, and decreasing. So this first term, let's see, I'll just put n and then n plus 1 and n plus 2 and so on, n plus 3. So I want to show that the improper integral from n plus 1 to infinity is less than or equal to r sub n. So if I construct my rectangles this way, so that the rectangles are partially above the curve, okay, so in this picture, the area of this first rectangle, well, the height is a sub n plus 1. The base length is 1. So the area of this is a sub n plus 1. The area of the next rectangle is a sub n plus 2, and so on. And from n plus 1 to infinity, the graph of f of x is below the tops of those rectangles. And so we're starting at n plus 1. So the improper integral, I guess I can write it down here. The improper integral of n plus 1 to infinity of f of x dx is less than a sub n plus 1 plus a sub n plus 2, and so on. But a sub n plus 1 plus a sub n plus 2 and so on is what r sub n is. So this argues pictorially why this inequality holds on the left. Hey, then the inequality on the right, so I'll draw another picture. So we'll start at n, then go to n plus 1 and n plus 2 and so on. So this time the rectangles, the tops of the rectangles will be below the curve. Okay, the area of this first rectangle is a sub n plus 1. We're using the right endpoint to determine the height of that rectangle. The area of the next rectangle is a sub n plus 2, and then a sub n plus 3, and so on. And so the sum of the areas of those rectangles is less than the improper integral of f of x from n to infinity. So r sub n, which is a sub n plus 1 plus a sub n plus 2, and so on, is less than the improper integral from n to infinity of f of x dx. Okay, so remember what r sub n is. This is s minus s sub n. So if we add s sub n to all three parts, then we get this inequality at the bottom of the page. So s, which is the sum of the infinite series, is between s sub n plus the improper integral of f of x from n plus 1 to infinity, and then the larger value is s sub n plus the improper integral of f of x from n to infinity. Okay, we'll use this idea. I'll just make another comment about this. A way to get a better approximation than s sub n is to take the midpoint of the interval that's determined by the left number and the right number. So in other words, if you take the average of this number on the left and the number on the right, the average of those two numbers will be a better approximation than s sub n is. If that's not clear, maybe in our example it will be more clear. Okay, so here's our example. Okay, we're going to use a known number. The famous mathematician Leonard Euler calculated that the exact sum of the infinite series of 1 over n to the second is equal to pi to the second divided by 6, which is approximately 1.644934067. So in this exercise, we're going to find the partial sum s sub 10, where the a sub n terms are 1 over n squared. And then we'll estimate the error in using s sub 10 as an approximation. Okay, so what's s sub 10? Well, when n is 1, 1 over 1 squared is 1. So I'll just write these down real quick. 1 plus 1/4 plus 1/9 plus 1/16 plus 1/25 plus 1/36 plus 1/49 plus 1/64 plus 1 over 81 plus 1 over 100. And this turns out to be about 1.644934067. So you can see that s sub 10 is a pretty good approximation of the actual value. Whoops, I wrote down the wrong one though. Sorry. That's the exact number. S sub 10, adding those 10 terms is 1.5497677731. Okay. So it's a little off, but pretty close. So what's the error? The definition of the error?
S minus S sub n.
Yeah, R sub 10 is the error. In R sub 10 is defined to be S minus S sub 10. So we know what S is approximately, and S minus S sub 10. So when we subtract those, we get 0.09516633358. So the error is less than 1/10. Okay, in the next part, we'll use this inequality that we saw on the previous page to get a better approximation. So when n is 10, we have S sub 10 plus the indefinite integral from 11 to infinity. Our f of x is 1 over x squared dx. And this is less than the actual sum s, which is less than s sub n, which is s sub 10 plus the improper integral from 10 to infinity of 1 over x squared dx. So up here, let's find what the improper integral of 1 over x squared dx from 11 to infinity is. So I'll give you a minute or two. You can tell me what that's equal to. And then after that, we'll find the improper integral of 1 over x squared from 10 to infinity. Anybody got it? How about the one from 11 to infinity?
1/11?
1/11th, yeah. So an antiderivative of 1 over x squared is negative 1 over x. So, okay, I'll go ahead and do it. Negative 1 over x from, this isn't the right way to do it, but from 11 to infinity. This is going to be 0, and then it's 0 minus negative 1 over 11th, or 1/11th. This one's going to turn out to be 1/10. Are we all in agreement? Okay, so this one, so S sub 10, we found that to be 1.549767731. So when I'll write it as s sub 10 plus 1/11 is less than or equal to s, which is less than or equal to s sub 10 plus 1/10. And then when you use the decimal numbers, the number on the left is 1.640676822. That's less than s. And the number on the right is 1.649767731. Okay, but to get a better approximation using these numbers, just take the average of the number on the left and the number on the right. So add those together and divide by 2. I'll just write it as the average of the endpoints is 1.6452222 and so on. I just took the average of those two numbers to get a better approximation. When you compare that with the actual number, you can see that it's pretty close. The actual number is up here. Okay, the next thing, find a value n so that the error in the approximation s is approximately equal to s sub n is less than 1/1000th. Okay, so the indefinite integral from n to infinity of 1 over x squared dx. Well, we've already done the work. This should be equal to 1 over n. And so the error, r sub n, is less than 1 over n. And so what we want is 1 over n to be less than 0.001. And when we solve this for n, what do we get? 0.001 can be written as 1 over 1,000. Yeah, so if n is greater than 1,000, if you solve this inequality for n, you get n greater than 1,000. So if n is greater than 1,000, then the error in the approximation for s of n will be less than 1/1000. Okay, let's take a look at some infinite series. So each of these, the integral test can be applied. You can see that the individual terms in the a sub n are decreasing, right? This is a sub 1 and then a sub 2 and so on. It's decreasing, so the integral test we'll be able to use for this. But you can also note that this is 1 plus 1 over 2 to the third plus 1 over 3 to the third, and so on. So how would you define it as an infinite series? Well, if n starts at 1 and goes to infinity, then the individual terms are 1 over n to the third. So depending upon the directions you see on a test, for example, if it just says determine if this infinite series is convergent or divergent, then if you recognize this as a p-series and p is greater than 1, then you can just say this series converges. On the other hand, the directions might say, use the integral test to show that this converges. And then you would have to show the work. Okay, we have a couple of minutes left. What about this one? 1/5 plus 1/7 plus 1/9. The individual terms are getting smaller in the a sub n sequence. So the integral test could be used. This is not a p-series, though. Notice that each of the denominators increase by 2. So that gives you a hint that the denominator has a 2 times n in it. So let's see, when n is 1, 2 times 1 is 2 plus 3. So I'm going to try it, 1 over 2n plus 3. When n is 2, 2 times 2 plus 3 is 7. Yeah, so this appears to work. This is not a p-series, but you can use the integral test. So compute this improper integral. If this improper integral converges, then so does the infinite series. If the improper integral, what's the other one? What did I say first? Converges? Yeah, but if it diverges, then the infinite series diverges. So you can compute that integral. We have a few more seconds. This one can also be tested using the integral test. It's not a p-series, but we're out of time. So tomorrow we'll be in section 11.4.